Hey there, everybody. How you doing? Welcome. We're going to talk about some limits today. Thanks for showing up. Here we go. First up, we're going to, if I were you, I'd pause this. I would write down that graph, and then what we're going to do is we're going to go through all the different limits that we could take from this graph. This is a nice review that we're going to use to kind of relearn some ideas or learn from the first time. All right, so this is chapter 1 in the Larson textbook. Here we go. Hope you paused. Welcome back. We're going to first look at the limits as x approaches 2. So that is right here. So as we think about that limit as x approaches 2, I look at it and I say, you know what? From the left side it approaches, let's make this exactly 4. So from the left it's approaching 4, and from the right it's approaching 4. So it's going to approach 4. That's kind of boring. Now, there's one... let's do it. So a limit of f of x as x goes to 3. As I look at as x goes to 3, here I am. The question is, do I choose the black dots or the whole? Well, what we do is we look at this and we say, you know what? From the left, what does my function approach? It approaches 2. Okay, so you have a height of 2 here. And what does it approach from the right side? It also approaches 2. So from the left it approaches 2, and from the right it approaches 2. So the limit, as I get closer and closer and closer to that, approaches 2. Now, you're saying to yourself, but it doesn't exist at 2. That's okay. Because if I were to think of a graph, and it has a hole here, it's empty, okay? It approaches a value from both of these sides. And even if there's nothing there, you can approach it infinitely close, and you'll get closer and closer to it, and that's okay. It's okay that it's not there. Now, this is, I think, a question that will make you at ease. What is f of 3? F of 3 is not 2. There's a hole there. What is the f of 3? 1. Okay. The example I always thought of is I have a mountain. Okay, and right here there's a cave. Look, it's a hole. And as I'm hiking up the mountain, I'm like, I wonder what altitude this hole is at. I wonder what altitude the hole's at if I come down the mountain this way at it. This is called the intermediate value theorem. That at that hole, it's not intermediate value theorem. Let's hold off on that for today. That hole is where it would be if the hole had something in it. Now, even though the cave is here, what I'm saying is the ground, if it was there, would be that high. Now, f of 3 is saying, how high is the ground? The ground is not at the height of the hole. It's somewhere different. And that's okay. Now, we're going to go to the next one. Limit as x goes to 4. From the left side, it approaches 1. From the right side, it approaches -1. Well, that doesn't approach the same value, so we would say that the limit does not exist. But if I look at it, what is the limit as x approaches 4 from the left? It approaches 1. What is the limit as x approaches 4 from the right? It approaches -1. Another good example that I've learned is a good one is this. What we're going to do is we're going to look at what the limit as x approaches 0 from the left is, from the right is, and what the limit is. Okay? So if I think about square root of x, okay, there's my function. It's very important that you realize this, that it has no negative values. Its domain does not allow it. So can I take the limit from the left? Nope. So I would say it does not exist. It doesn't exist. How about from the right? What does it approach? 0. Because if you look at this function, does it approach 0? Yes. So what does the limit approach altogether? It does not exist because of no negative values. So there's idea 1. Next, we're going to look at functions that are non-continuous or at least have steps in them. So we'll deal with this one on the right side first. The left side one is a new to a lot of you. It's called the greatest integer function. We'll come back to that. So what we're going to do is we're going to think about this here. I've got two functions, one up above, x squared minus 3 and 3x minus 8. Well, we're going to do our first limit here. As x approaches 1 from the left. Well, from the left side, it is less than 1. So I am dealing with this function. This is from the left. Well, what does this guy approach from the left? Well, to find out, I plug in 1. I know it doesn't exist at 1 because it's just less than, but I'm going to plug it in to see what value it approaches. So I plug it in, I get 1 squared minus 3, which is negative 2. So what does it approach from the left? Negative 2. Now, what does it approach from the right side? Well, from the right side, this greater than or equal to 1 is from the right. Okay, and so if I plug it into that one, 3 times 1 minus 8 is negative 5. So what does it approach from the right? Negative 5. Are those the same? No. So if you think of your function, as it gets to 1, it approaches negative 2 from the left, and it approaches negative 5 from the right. That is a solid dot, and this is a hole. And do these meet? Do they meet up? No. And so I say my limit does not exist. And the other thing that I can also say is not continuous. And this last question I think will kind of fill in some gaps. What's f of 1? Well, doesn't exist at less than 1. It only exists in the right side one, on the bottom one, 3x minus 8. So it's 3 times 1 minus 8, which is negative 5. All right, left side, greatest integer function. Greatest integer function has the sweetest, no idea what just happened, sweetest graph in town. And so its graph is, how about this? Let's build it. We will make this graph. You can just Google it. Google is a fascinating tool. They own the internet. Okay, Al Gore made it. Google uses it. So greatest integer function. Let's do this first one. Now, 1.9999. That the greatest integer in that number is 1. Has it reached 2 yet? No. So I would say my greatest integer is 1. How about the next guy? F of 2.0001. Well, my greatest integer is 2 because I am 2. And so 2.6 would be the greatest integer. So the way you'd write this is the greatest integer of 2.6. Well, what's the greatest integer involved with 2.6? 2. So what's weird is my graph. So when I was at 2.000, that is the greatest integer, goes all the way up, and then I'm going to have a hole here. Now, 1 goes up, and we have a hole at 2, because when I get to 2, I'm up here. I'm on a new step. So we call these step functions because it takes steps. So what is the limit as x approaches 2 from the left? Well, that means it's less than 2, so it approaches 1. What is the limit as x approaches 2 from the right? 2. So what is the limit as x approaches 2 of a greatest integer function? Does not exist because they're not the same value. So it doesn't exist. Now, another thing we do is we use limits to force continuity. They'll say what value of k would guarantee continuity. So the idea is to be continuous that my functions have to meet up. No matter what the functions look like, but when they get to 2, they have to meet. And for them to meet, well, that means when I plug in 2 into each of them, that they're going to equal. So 2 squared minus 3 is 4 minus 3, which is 1. So f of x is going to go to 1. Well, this guy, if I plug in 2, I get 5 times 2 plus k. So that's 10 plus k when I'm at f of 2. This is from the right side. And so I need 1 and 10 plus k to match up. And so I could say negative I equals k. That would force them to be continuous. Next up, working with trig problems. This is something I've noticed is an issue with a lot of people, and so let's just talk about it. It's the elephant in the room. Trig. I know you don't like it. You should. It's great. You can do cool stuff with it. Sine of x over x. As x approaches 0, it approaches 1. If you have this in your calculator, you'll see that. Okay, it's very important. I think it'd be really nice. Just graph that, and you'll see it. Okay. Next up, how about sine of 4x over x? Now, this one I've learned people don't like. Here's why. Because they're like, but I don't know what to do. Well, watch this. If I put a 4 here, right? If I put a 4 on the bottom, I gotta stick a 4 on the top. Let's just get that out in the open. All right. What does sine of 4x over 4x equal? Well, it equals. It approaches 1. And so what happens if I stick that? I still have my 4 out front. So what's the limit of that? 4. Now, us calculus teachers really like to give you this one. We go, haha, sine squared x, sine squared of theta. Whoa, I'm mixing stuff here. This should be x. I'm sorry, guys. If you caught that, nice job. And so this is going to be sine squared of x, because 1 minus cosine squared of x is sine squared x. Please know that. That's really good for you. Rewrite this. Here's why. This is sine of x times sine of x divided by 2 times x. Well, what does sine of x over x approach? It approaches 1. Right? What does sine of 0 equal when I plug it in? Think about it. 0. So what is my limit? Sure. If you graph it, you'll get the exact same answer. Next one. This is a really good one. Is here we go. Limit as x goes to 0. Now, anytime you see something that you can factor or work with, factor it. Work with it. I'm going to factor an x out, and I'm left with x minus 3. Okay. What does sine x over x approach? 1. Okay. And so this is going to go to 1. Well, what is this guy on the right side going to go to? This guy on the right side, it's going to go to 1 divided by 0 minus 3. Just evaluate it. Stick it in. And so what's 1 divided by minus 3? Got it. A little case of the Mondays for you. So it's just 1 over negative 3. Okay. Very good problems. Always be looking for trig substitution. The biggest one is right here. Let me highlight it so we're all looking at the same stuff. As I'm staring at the screen. This guy right here, know that. Know that, know that, know that. The next one is 1 minus cosine squared x goes to, is equal to sine squared of x. Okay. Those two identities alone are going to really help you out. So there it is, guys. Hey, thanks for tuning in.